Hello, welcome to another edition of Mr. Murphy's Science Classroom. And last time we were talking, we discussed measurement. So today we're going to continue on with that same topic of measurement. And we're going to finish it up with a couple of additions to the PowerPoint. Last time we ended with this slide and we were talking about Archimedes, and we discussed that he figured out that the volume of the fluid that is displaced when an object is submerged, right, is its volume or is equal to its volume. So he called that the displacement method. So that material, right, we can take it into a beaker or into something and actually measure it, and that would be the volume of the object we placed in it. The demonstration in the demo video explains that and talks about that. So catch that demo video. It will be up shortly if it's not up already. So we're going to move on, and the next thing we're going to talk about is with the graduated cylinder, or measurement with the graduated cylinder. If you look on the right-hand side of the screen, I have a graduated cylinder here. And if we were to take that material that was dumped out of the tub and put it into a graduated cylinder, we'd be able to measure its volume. And this is what we use to do that. If you look at this, right, where you can see it's measured in milliliters. This is a 250 milliliter beaker. I have a 50, and I also have 100 here. And in the demo video that I spoke about previously, I use both of those to work the displacement method. When you're reading the graduated cylinder, the biggest thing you have to remember is you have to get right even with the lines on there and take a look at where the meniscus is, or that little dip in the water. Make sure you're measuring to the bottom of that because that's the most accurate way to measure. Next thing we're going to talk about is how to calculate the actual volume using the volume formula, length times width times height. If you look at the cube to the right, you can see that the length and the width are 10 centimeters and 10 centimeters, respectively. And the height is also 10 centimeters. So this is considered a perfect cube because all the sides are the same length. When you multiply the numbers out, you get 10 times 10, which is 100, and then 100 times 10, which is 1,000. And that's the answer they have there. If you notice, right, they have centimeters cubed. Well, that's what comes out of when you measure, or when you multiply centimeters times centimeters times centimeters, it would equal centimeters cubed. And so that cubic centimeter, and I talked about this in the demo video as well, that 1 cubic centimeter is equal to 1 milliliter. So if I had a 1 centimeter cubed, I'd be able to put 1 milliliter right inside that cube. And so when you think about cubic centimeters, you have to think about it as milliliters too. So when you're trying to figure out density or trying to prove that Archimedes' volume displacement method works, if you used a regular object like I do in the demo, you'll notice that the volumes come out almost perfectly the same. Obviously, with a little experimental error, it may not be perfect, but it does a pretty good job of showing that cubic centimeters is equal to, or at least close to equal to, the actual volume, or 1 milliliter. So now we're going to measure, now we're going to talk about temperature. And when we use a thermometer, what does a thermometer give us? What is temperature? And if you notice in the definition here, we talk about the degree or intensity of heat present in a substance or object. Well, now we have to talk about heat. And what is heat? Heat, right, is energy. So the energy that is present in an object or a substance is going to be equal to its temperature. Now, we measure this with a thermometer. So when you think about what are we finding with a thermometer, you always think, oh, temperature. But we're actually measuring the amount of heat. Now, when we're talking about heat, if you think about an object, when you heat the object up, what happens? Well, the molecules start moving faster. And if you heat it even more, they move faster than that. So let's take the example of ice. Right? Ice is frozen water, and it's in cube form. It doesn't have to be. But when we add heat to that, right, the structure of the solid, right, starts moving around, and the atoms and molecules move around. And as they do that, right, they start freeing themselves up and start moving around. And then we have water, the liquid form. Once that gets all melted, then the temperature will start to increase as we continue, right, to add heat to that experiment. And later on, we'll talk about we'll talk about how that functions, and we'll actually do a lab on that. When you look at after the water, right, and we still keep adding heat to it, eventually those molecules get so excited that they pop out into the air and create water vapor in the air, and that's a gas. So that movement of particles, right, that movement of particles or heat energy, right, can also be known as kinetic energy, because kinetic energy is the energy of moving particles or moving things. So when anything is in motion, right, it has kinetic energy. So looking at the thermometer here in this picture, I'm going to slide down just a little bit so you can see it. Looking at the thermometer, you'll see that there's a liquid inside the thermometer, and it's sealed inside there. So if heat, right, if we place this near a warmer object, these molecules inside this bulb will start moving faster and faster. Eventually, they'll want to escape. Well, the only way they can escape is up through this thin, narrow tube up through the center of the thermometer. And therefore, right, the more heat that's applied, the more excited the molecules and atoms get, and therefore they will start moving up that tube and give us our temperature. And so that's kind of how a thermometer works. And again, heat, right? Heat energy is also considered kinetic energy. So now we're talking about air pressure. So now that we've got these air molecules all moving around us, and the force of that air on us, right? Because it also has, gravity, it's influenced by gravity. So that force of that air pressure on us, right, is consistent or constant. Because if it pushed us at one side, we'd actually fall down, which wouldn't be any fun because you wouldn't be able to get up. It would keep you holding, keep holding you to the ground. But the air pressure, right, the air pressure that we feel is measured by a barometer. And there's a couple of different kinds of barometers. The mercury barometer, and then there's the aneroid, which is the one you can see pictured in the slide here. The aneroid barometer works on mechanical pieces or parts. And so when pressure is exerted on one of those parts, it moves the dial around. A mercury barometer is based on the actual air pressure pushing down on the mercury and pushing up a tube that looks like a graduated cylinder upside down and pushes it up, and that's measured in inches. We usually measure air pressure in millibars. This aneroid barometer, however, measures it in hectopascals and millimeters, but that's fine for now. And just remember that we'll use millibars. And on page 13 or 14 in the reference tables in the weather section, it will have a conversion chart and explain the conversion between millibars and inches. So as you look through that, make sure as you look through the Earth Science reference tables, make sure you check those diagrams out, because it also has temperature conversions from Fahrenheit to Celsius to Kelvin, so that you don't have to do those calculations and to make the conversions. You can just look across the chart and be able to figure it out. Now, air pressure. Think about a balloon. You blow up a balloon, and the balloon is sitting here, and the air, right, is pushing from inside the balloon out, and that's what gives it shape. But also, at the same time, there's air pressure pushing in, right, in all directions on that balloon. So as that balloon keeps growing, in other words, if you put more air in the balloon, right, it will expand. As that air expands, right, it gets to a point where that balloon can't handle it anymore, and it will burst. If you let go of the balloon, once you blow it up and it goes, right, and falls to the floor, you have opened the air pressure from the inside. You have let that air pressure out. And so what happens is the air pressure on the outside squeezes that balloon closed and pushes all the air out of the inside of it. So if the air pressure is greater on the outside, because you open the nozzle on the bottom, right, it will squeeze that balloon down. And we'll talk a little bit more about air pressure, in the high altitude classes, if you're interested in that. Like I said, we're going to have Zoom meets and things like that with some very cool people. And we'll be talking about launching balloons, and we'll talk about payloads. So that's basically what it is about air pressure. That is the end of the measurement section. We'll be moving on to density, which is a comparison between mass and volume. And so you should remember these slides from that. By Thursday, we're going to have a quiz, and it'll be based on what we've seen so far in this slideshow and the previous slideshow on observation and inference. All right, so make sure you look out for that quiz. Make sure you complete these notes, and have a good day. Stay safe.